everybody. This is Miss List, and I am here with 4.8. From AP Chem, this is acid and base reactions. So, some of this we've already talked about when we did acid and base introduction in the other sections, but there's a little bit more that we're going to add to this. So, over on the right, we have our three definitions of acids and bases. And it started off very simple that acids had hydrogen and bases have hydroxide. This is what we call the Arrhenius definition. That is usually how students first learn acids and bases. The definition that we are going to be focusing on is going to be the Bronsted-Lowry definition. That is the one that we use most often in AP Chem, and that's the one that I was talking about in the last section where I said that hydrogen donors are the acids and hydrogen acceptors are the base. There is another definition, Lewis definition, and that's the same Lewis as Lewis dot structures. It says that an acid is anything that can accept an electron pair and anything that can donate electron pair. This definition comes up a lot in organic chemistry because we don't have water as a solvent. The reason that we use Bronsted-Lowry the most is because we have water as a solvent. So if we focus in on the Bronsted-Lowry definition of acids and bases, this is where we get the acid is going to be the proton donor, and a proton is another way to say a hydrogen ion. Once that transfer happens, it becomes the conjugate base. So the acid becomes the conjugate base. And we can see that here in our example. We have HA, which is usually a generic acid. And we can see that that hydrogen that I'm circling is being transferred over to water, which is acting like a base. That's why water becomes H3O, because it gains that hydrogen. And then the HA, once that hydrogen is gone, is simply just A minus, and that is our conjugate base. Our base, once it accepts the hydrogen, then it becomes the conjugate acid. So we have this role reversal. The acid becomes the conjugate base, and the base becomes the conjugate acid. Oftentimes, it's important to know whether we're dealing with a strong acid or a base or a weak acid or a base. I mentioned this in the last video. We are not talking about molarity here. When we talk about a strong acid or a strong base, we're talking about how much it ionizes. A weak acid or weak base is going to ionize only a fraction of an amount. A strong acid or base will completely ionize. And what do we mean when we say it will completely ionize? Is that it will break apart 100% into hydrogen ion and it's an ion. So this happens only when we have a strong acid 100% of the time. If I have a weak acid or a weak base, then only a fraction of the molecules will split up, and it's usually a very small fraction. So down here in this example, we have kind of what I was showing with the hydrochloric acid. When I put hydrochloric acid in water, water acts as the base, and I'm going to transfer the hydrogen over to water and form what's called a hydronium ion, or H3O+. And that is the acid component, and then the chlorine ends up by itself. This happens 100% of the time, and that's why we use a single arrow to show that this happens completely. However, when we have a weak acid, that means that it is not going to happen 100%. And so we have an equilibrium system that gets established, and that's why we use the double-sided arrow, is because we have an equilibrium. Now, we can also use the strength of acids and bases to determine how strong or weak the conjugate will be. So if I have a strong acid, then my conjugate is going to be weak, and then vice versa. So if I have a weak acid, then its conjugate is going to be strong. And that helps, again, some of these topics will come up in Unit 8 when we do a deep dive on acids and bases. This is simply an introduction. Now, so we know that strong acids 100% ionize, weak acids don't, but how do we know if it is strong or weak? That, unfortunately, is some memorization. If it's not on this list, then it's considered weak. So a good rule of thumb is to memorize the strong acids. Similarly with the bases tend to be group 1 and group 2 hydroxides. If they're not on this list, then they'd be considered a weak base. And unfortunately, there's not any real good way to know this. This is something that you would just need to memorize. Final thing that I want to just mention here, again, this comes up later when we do acid base in unit 8. But when I have an acid plus a strong base, so this would be strong plus strong, the net ionic for a strong plus strong will always be the formation of water. And that's because our spectator ions cancel. So we have this 100% ionization, and if they're both strong, that means that HCl is going to break up, and that happens 100% of the time. And KOH is going to break up 100% of the time. KCl is also going to be separate because remember, our SNAP ions are always soluble. And so that allows me to cancel the chlorines and the potassiums on both sides. And what's left is literally H plus OH goes to water. This is going to be the net ionic equation anytime I have a strong acid plus a strong base. Now, this will not be the case if we have a weak acid or a weak base, and we will talk about those again in Unit 8. This is just an introduction to acid-base definitions, what makes something weak or strong, and the net ionic if they're both strong. There's actually not any practice problems for this section because it's basically a carryover from what we were looking at in the last section with that conjugate acid-base definitions and identifying who the conjugate is. We will revisit this in Unit 8 when we do our deep dive on acids and bases and equilibrium. All right, y'all, thanks for listening, and I will see you next time.